We're back. Okay, here we go. Go. I took a break, got some coffee. Woohoo! Bumped. All right. You can see on the sheet for this week, this is us, or this meeting. I say this week because I'm typically used to meeting once a week, but this is what we'll be doing tonight. And you can see that we have acceleration due to gravity on there and then gravitational acceleration problems. So, acceleration due to gravity. Okay, you know you drop things, they speed up, they accelerate, right? You know that. So acceleration due to gravity is also what our lab is going to be on. Okay, our lab for today is going to be on acceleration due to gravity. We'll use a very accurate stopwatch. We'll use a computer to do some timing for us, and you will be my lab partner. But we know that things accelerate due to gravity. We also know they decelerate due to gravity. We all know that what goes up must, very good, Michelle, come down. All right, must goes up, must go. Unless you pump that thing up at what's called escape velocity, like 25,000 something miles an hour, it's coming back. Okay, and most things don't travel that fast. So, I mean, I used to be able to throw things at about 28,000 miles an hour. I could get them to escape, but I'm getting older now, so I can only throw them about 20,000. So they come back. Okay, so things go up, they come back down. I'm not going to get terminal velocity. I'll talk about terminal velocity a little bit later. There is something called terminal velocity. You've heard of that before. And that does have some influence on some of our up and down problems. But we'll leave terminal velocity out for the moment. We'll assume that our problems have no friction in them. Terminal velocity is actually a form of friction. So we will not include that yet. We will, but not yet. Okay, so what is this acceleration due to gravity you speak of? All right, there's this guy, smart guy. His name was Aristotle. You've heard of Aristotle. He's one of the philosophizers. You know Aristotle, Socrates, Plato, okay, all those smart philosophizer Greek guys back in the day. And they used to sit around and think. And then they'd come up with, aha! And they'd write it down, and people go, ooh, you were so smart. And people go, yeah, this guy's a smart guy, so what do I know? He knows, I'll believe him. And Aristotle, say it correctly, Aristotle, the philosophizer. Oh, so now McClure, now you're a philosophizer. Okay? Dodgeball 2005. So quotable. Great quotable movie. Okay? Philosophizer. Where was I? I'm off tangent. Where was I? Aristotle. Okay. So he said that things that are lighter fall slower. Okay, he's making observations. You saw that. I mean, it's not really scientific, but he was making, at least he's doing some observations around him and coming to some conclusions. He didn't test everything. He didn't test all the variables. But he said, if I take this, you're not going to be able to see this, but just try this at home, okay? Not for professionals only. Sheet of paper, marker. Well, you could see that. The sheet of paper already was behind. The marker being heavier. The marker being heavier fell faster. Aristotle is right. The paper being lighter, this is actually a napkin, fell slower. So smart you are, Aristotle. All right, but along about 2,000 years later, a guy by the name of Galileo. Galileo, you've heard of him, right? Yeah. Galileo got in some trouble with the church because he was doing the science stuff and they didn't like it, and then he was like house arrest and it was a mess. But anyways, one of the things that he did, Galileo. Oh, in Galileo, there's also a Paladin tank on World of Warcraft. My guy, yeah. Oh, I'm a nerd. Oh, I am a nerd. I'm a geek. Oh, yeah, you bet it. Where was I? Oh, yeah. So Galileo, what he did, of course, I mean, who knows if he really did this, right? I mean, they wrote it down. He wrote it down. He said he did this. So I'm going to trust him. He wrote it down. He said he went to the Tower of Pisa, which at that point was not leaning, okay? It was called the Tower of Pisa. It wasn't leaning yet. Okay. And he ordered some pepperoni and some mushroom. Tower of Pizza. Sorry. So he went to the top of the tower, and he took a piece of lead cannonball, and he took some lead shot, like it's called grape shot, little lead balls, a lead canister. That was nasty stuff comes out of a cannon. So some small pieces of lead, round, large pieces of lead, round, went to the edge, and he had an assistant down below, and the assistant went, ready, go ahead, okay, ready to catch them. And he dropped them, same time, boom. And he wanted to observe which one hit the ground first. Well, who won? Same time, same time. What was Galileo doing? He was taking the air resistance factor out. The piece of paper doesn't hit the ground first or at the same time as the marker because it has the air resistance behind it. If we disregard air resistance, everything should fall at the same rate. And if you do this in a vacuum, and they did this on the moon, Apollo 14, they took, you can YouTube it, they took a hammer and a feather on the moon and boom. Nowadays, of course, they have vacuum chambers you can do this in. And without air resistance, everything falls at the same rate. All right, thinking. What is that rate? Okay. Well, we'll experimentally determine that today, but we're going to need to know, Ed. So I'm just going to tell you. I mean, you kids are relatively smart people out there, so you can look it up. It's 9.8, so write this down. You're going to need it. 9.8 G. I'll call it little g. Little g, because there is a big G. There is a big G, and we have a little g. Little g is 9.8 meters per second squared. Notice the units. It's an acceleration, but it's an acceleration due to gravity. Everything near the surface of the Earth will accelerate toward the center of the Earth. That's where everything wants to go, toward the center of the Earth at that acceleration rate, 9.8 meters per second squared. All right, so that's important because we now know if anything is going up and coming back down, this factor is acting on it to slow it down and speed it up. What goes up must come down. What's the acceleration of something going up? Negative 9.8. What's the acceleration of something coming down? Positive 9.8. So if you toss something in the air, gravity's working on it on the way up and on the way down. Should take the same amount of time to go up and come down, disregarding air resistance. Disregarding air resistance. Okay, so same time up and same time down. That's an important concept we need to know as well. All right, so now the big three, we're going to have big three equations using gravity. Well, that's a little g and that's an a. Oh man, we need new equations. These equations worked back and forth, horizontal. Very good, Winston, very good. But they're not going to work up and down, are they? We need new equations. No, Winston, no. Really? Yeah. The same equations work up and down and back and forth. The only difference is now we know the acceleration rate when we're talking up and down. We know that this A is now going to be a little g. So that's what I like to do. Just take that A and make it into a little g. And so we have that. That's known all the time. So we don't have to have as much information given to us in a problem because we know that piece already. Okay. I will tell my students when something is going up, use positive 9.8. When something is, no. Up, negative, and down, positive. That's what I like to tell my students. The other way around is done a lot of times in textbooks, and here's why. First of all, let me explain why I do it this way. If something's going up, slowing down, right? Slowing down. So I say use a negative to indicate that it's decelerating on the way up. And when it's coming down, use a positive, it's speeding up. Sometimes you'll see in textbooks or in papers, physics papers, they will use the negative going down and the positive going up. Well, why do they do that? That's stupid. Well, they do that because of the y-axis. Remember the y-axis? Yeah, x, y, and z actually coming out at you. Y-axis, positive y is up. Going up. Negative y is down. That's why. You'll see that sometimes. I don't like it because then you got to think about when you put in the equation what you're getting for an answer. You're going to be getting a number value opposite of the direction. It becomes confusing. So negative going up, positive coming down. All right. Makes it easier. Let's do a problem. Battling on again. That ancient city joke. Fred drops a dinosaur burger. Have you noticed something here? Betty, Wilma, Fred. Next question is Barney, and then there's Pebbles. Flintstones. Yeah, some of you get it. All right. Fred drops a dinosaur bone from the top of a 75-meter high cliff. So he drops a dinosaur bone. What's the initial velocity of the dinosaur bone? 0. Initial velocity of the dinosaur bone is 0. He drops it from a height of 75 meters. So the distance where it's going to fall, 75 meters. Okay, that's it. That's all we're given. Oh, we can't do this problem. We can't do it. You said in the last video that you have to have 3 known things to use a big 3. That's it. We only got 2. We only have that. That's it. We're done. We're done. No, what did I just say? We have the acceleration rate because it's falling. We're assuming that the Flintstones are on the planet Earth. They are. I've seen them personally. So we know that the acceleration rate, now I'm going to make that a little g, is 9.8. And it's falling, so it'll be a positive 9.8 going down. Okay, what do we need to figure out? How fast is the dinosaur bone going as it strikes the ground? I sometimes students are like, well, 0 strikes the ground, it stops. No. As it strikes the ground. Impact velocity. Final velocity before it stops. So we're trying to figure this bad area out right there. Looks like this is going to work. Now, we haven't even used this one yet, have we? Well, we will, don't you worry. This one's going to work. Final velocity is equal to initial velocity 0. Again, it's a 0. A is 9.8 times time. Oh, yeah. Not so fast, Ricky. We don't have the time. You can't do that equation and figure out this velocity without a time. Oh, man. What about this one here? This will work, right? Because you have 75 and 0 and 9.8. No time. Aha. Now we are actually going to use the bottom one. We haven't used it yet. Using it now. This bad Larry here is when you have no time. No time. You might have some parsley, some sage, some rosemary, but no time. Spice joke. Spice joke. Spice Girls. So hot. All right, now. There's no time here. Okay. Did you get my spice joke? All right. So you have the information to solve this one. And it's already set up for VF, which is what we're trying to find anyways. Nice. So let's go ahead and use it. Square root of VI squared. Well, VI is 0. And 0 times 0 is 0. 2. G is 9.8. Distance, 75 meters of foliage. I like that word, foliage. Good word, I made it up. Now, if you multiply this out, let's check this out. It's going to be like 20 times that, so 75, so 150. Square root of 150. Between 12 and 13. It'll be going between 12 and 13, okay? 12 and 13, that is my guesstimation here. 75 times 9.8 times 2. Square root that. Second function, answer. Oh, I was close. I said between 12 and 13. Let's make sure I did this right. 75, 9.8 times 2. Yep, got it. Square root, 38 meters per second. Should that make sense? That makes sense. How did I put 12? 13. That was stupid. All right, yeah, because think about this, okay? You're falling from 75 meters. 75 meters is a long way. That's 150, 220. That's like 22 stories. That'd be like a 22-story building. When something is falling out of a 22-story building, it's going to impact the ground pretty fast. Not 12 meters per second, like my stupid quick math did without my calculator. I should use my calculator. That would only be 24 miles an hour. That's nothing. You could laugh at that. You ain't laughing when you hit the ground going 38.3 meters per second. So 38.3 meters per second. Remember how fast that is? Miles per hour. Double it, add a little bit. So you're looking at 76, about 80 miles an hour. Yeah, you ain't laughing when you hit the ground at 80 miles an hour. Unless you're Iron Man. Okay. All right, so that's how fast the dinosaur bone would hit the ground. Now, is there anything else to this problem? How long? How long will it take for the bone to fall to the ground? So how long take? So we have to figure out this one right now. Now we know the final velocity is 38.3, so we can put that in. Trying to find time. So I can't use this equation because there doesn't any time. Remember we did the whole spice joke, it was funny. And this one I can use. This one has a squared thing in it. This one looks a little simpler for time, using that one. Final velocity is, we just figured it out, 38.3. Initial velocity was 0. Acceleration rate's 9.8. So that's plus 0, but it's just going to go away anyway, so I'm getting rid of it. Times time. All right, divide. 38.3 divided by 9.8, it's about 3.8 seconds. Because if you use 9.8, you can kind of look at it as 10. So a little bit more than 3.8 seconds. But let's do the math. Let's do the math. Accurate divided by 9.8. Boom! 3.91 seconds. Time equals 3.91 seconds. All right. So it takes about 4 seconds for it to fall and hit the ground without air resistance. There was no air resistance at all. Okay, that is that first problem. Pretty straightforward. You're just dropping things. Next problem. Let's get rid of these. I'm suspecting, if I remember right, I had something. Toss it in the air. Yes. Barney tosses a brontosaurus burger into the air with a velocity of 40 meters per second, about 86 miles an hour, 87 miles an hour. That's pretty good toss, okay? Pretty good throw. Maybe he's playing for the Red Sox. Not this season. Let's see, Barney tosses the brontosaurus burger in the air 40 meters per second. Okay, how high does the brontosaurus burger go? So initial velocity, this time the initial velocity is not 0. We're actually tossing it with the velocity of 40 meters per second. The final velocity, okay, here, be careful. So we're tossing. There's Barney, his brontosaurus burger, in the air, 40 meters per second. What has to happen to it? It's got to go up and stop. It has to stop at its peak, pinnacle, apex, and or zenith of its flight. It will, for an instant of time, we can debate what an instant is, but it will stop and then come down. So it's going to go stop and then come down. So the final velocity on the way up is 0. This is my initial velocity, and this is my final velocity. So the final velocity as it gets to its peak, pinnacle, apex, and or zenith is 0. We now also know that the g is a negative 9.8. Negative, it's going up, it's decelerating, use the negative. I don't know how high it's going. In fact, that's what the first question is asking. And the time, I don't know how long it's going to take it to happen. It's probably what the second question is going to ask. But let's figure out the first question first. Okay, which equation should I use? I have a final velocity, an initial velocity, and a gravity, and I need distance. That's not going to work. Don't have distance. This might work. I have an initial velocity, and I don't have time. I wasn't given time. In fact, let's check this. Yeah, how long will the burger be in the air? That's the second thing we have to figure out. We don't have it yet. You could actually figure out the time first if you wanted to. You could do the second part first, but I'm not going to do that. So I don't have time. Spice equation, parsley, sage, rosemary, no time. Okay, we're going to use this one. So now, this time I'm solving for distance. Ooh, we're going to have to dig deep into our algebra here and get that distance solved for. The final velocity as it goes up is 0. Square root of the initial velocity, which is 40. Algebra, nice. Squared, 40 squared, plus 2 times negative 9.8. I know, if you're not an algebra person, this one might be scaring you right now. But watch it, do it yourself, go back, watch it again. If you don't get it, do it yourself until you get it. Okay. Now, distance is unknown, so I plugged everything in. Final velocity goes up, stops. Threw it at 40, square it, plus 2 times negative 9.8 times d. Okay, how do you get rid of that square root? It's called a radical. How do you get rid of a radical? Put them in jail. Put them in jail. That's how you get rid of a radical. Okay. Yeah, square both sides. If you square this side, you got to square that side. Square 0, 0. That doesn't do anything, right? You square this side, 0, so that just stays 0. But if you square this, we just get rid of the square root. So really what we're doing here is just get rid of the square root, it goes away. Square both sides. Now if this were not 0, let's say maybe it was 20 or something, then of course we would have to square that, and 20 times 20, we get 400. But 0, so it stays 0 when we square it. Okay, keep going. Do the math. Now, so 0 equals square 4, 16, add a couple zeros. That's going to be 1,600. Now, plus negative 9.8 times 2. That's negative 19.6. Plus negative 19.6 D. Yeah, a little more algebra here. Whew. What we built up to, we warmed up. You know, we did a couple push-ups. Now we're doing some benching. Okay, we're warmed up and ready. Solve for D. I have to get D by itself. Isolate D, subtract 1,600 from both sides. Subtract 1,600 from this side, and it goes away. Subtract 1,600 from this side, it goes away. Subtract 1,600 from this side, 0 minus 1,600, and you get negative 1,600. Negative 1,600. All right. Isolate the D. This plus is gone. Negative 1,600 equals negative 19.6 D. So divide both sides by negative 19.6. So that goes away. And put that D here now, move it over. And divide this side by negative 19.6. Negatives cancel. So I'll get a positive answer for this. And last but not least, where's my, there it is. All right, 20, so 20 was 80, it's gonna be about 80 meters, looks like. 1600. I'm not trusting myself after that last one where I said 12 and the answer was 38, but I'm looking at 80 meters. Divide 19.6, 81.6, so that's good, 81.6 meters. So the distance will be 81.6 meters high. That's how far up that, we threw that thing pretty fast, so it ended up going 81.6 meters high. Okay, now let's get this one done. This is a long video. I don't like long videos over 20 minutes. I know you don't either. We're already over 20 minutes, but let's get her done. Okay, we'll go through this one kind of quick. How long will the burger be in the air before it comes back down to Barney's hand? So that means we're going to toss it up, and it's going to come back. Remember earlier, what goes up must come down. The time going up is equal to the time going down. So we just have to figure out how long it takes to go up or how long it takes to go down and double it. So time we don't know. Distance we know, 81.6. Final velocity going up is 0. Initial velocity was 40. G is negative 9.8. Let's solve for time. Let's figure out time. Can't use this one. Use this one or this one. All right, let's see. I'm going with this one. This is easier. Final velocity going up is 0. The initial velocity going up was 40 plus negative 9.8 times time. Okay, solve for t. Subtract 40 from both sides. This is going to be 0 minus 40 is negative 40. Negative 40 is equal to negative 9.8 times time. Divide by 9.8, both sides. So this goes away. Negative 9.8 divided by negative 9.8 is negative 9.8. Negatives cancel. You get a positive value. You always get a positive value for time. You always will. You can get negative values for some things, but not time. 40 divided by 9.8, a little bit more than 4 I'm going to round that to 4.1. So the time to go up is 4.1 seconds. Now that's not the answer because it wants the time to come back down to his hand all together. So it goes up 4.1 seconds, it'll come down at 4.1 seconds, disregarding air resistance. So double it, answer 8.2 seconds. Now, I apologize if some of you were bored out of your mind by the going through each algebra step, but some of you need that review. I know I've done this long enough where some of you are going to have trouble with the algebra. So please review again the algebra if you're getting stuck on it. If you have any problems on the algebra, make sure you stick around in the Zoom sessions when we have them at the end for extra help. All right, let's wrap this video up. This is a too long video, 25 minutes. You gotta be kidding me.